Yo. Oh, my cam's not working. Oh no. Let me fix that. Hold on. No. Oh no. I'm trying to fix it. Here we go. Webcam. Properties. Deactivate. Activate. Still not working. Oh no. No. Unplug. Replug. Go to the Logitech hub. It should be working. Let's activate it and reactivate it. Here we go. Deactivate. Activate. Boom. We're up. Whew. What's up, guys? How we going? Got the stream preview ready. Yeah, we got some new people in chat. We're ready to go. We got Ricky's here, Kate's here, Isaiah's here somewhere. I saw him going. Mr. Miraji's here, saying let's go. I made him a mod. I don't know if he knows what it is, but don't worry about it, sir. It's all good. Face cam up. Voice is working. Say hello if you're with me. And if you missed yesterday, I highly recommend you go back and watch that video. Right? Yo, we're good. Right, today we are looking at complex number in polar form, which you can see here. It's a very important lesson. Very important indeed. But I said yesterday that we were going to talk about radians first. Okay, so let's very briefly have a little look at this. So ignore everything on the left there. Let's just look at radians and degrees for a second, and understand this as well as we could. When I was at high school, I really struggled to understand this. I don't know why. My teacher was really good. I was just lazy, so I didn't pay attention. So if you pay attention, understand, then you'll be fine. So let's have a look at this. Right, I've drawn this beautiful diagram, and you can see. Let me get my little laser pointer. You can see here that I've got around here 180 degrees, which is this is what we explored yesterday. If this is all news to you, you should go back, exit this, go back to yesterday's video and watch that. But we explored that this is positive 180 degrees and this is negative 180 degrees. Right? Now, when we're talking about radians, let's change this color to like a off blue. This is not a very nice arc. There we go. This is positive pi. Okay, this is positive pi. And let's go like an off red. And have a guess what this is going to be. I bumped on the way. I want it to look kind of nice. That's kind of better. And this, my friends, is negative. Where's this pi here? Is negative pi. Okay, all the way around. I might even, yeah, you guys had a guess. You got a guess correct. I might put this over here, plus pi. And I might put the other one down the other end, just so you don't get confused, because that is actually pi by 2 right there. Negative pi, all the way around. Okay? So if we understand this, that pi by definition is 180 degrees, then we can do this conversion using a bit of our knowledge. So if you look down here, let's highlight this because it's important. If 180 degrees equals pi, then 1 degree must be pi by 180. All I've done is divided by 180 onto this side. So 1 degree must be pi by 180. So if you ever want to find out how many radians is x degrees, you can just multiply by pi by 180. Let's do 3 or 4 very quick examples, just so that we're all on the same page when it comes to this. Right? You should be able to do these very quickly yourself. Do it now, and give me 2 seconds to have a drink, and then I'll start it. So we're going to multiply these numbers by pi by 180, and you shall convert them into radians. So let's do the first one. 90 degrees, we times it by pi by 180. Now you could literally type this into your calculator and you'll get some gross decimal. But you could also think about it like this. 90 over 180 times by pi. 90 over 180 is a half, so this equals a half pi, which we often write as pi by 2. Do we agree? Mr. Maraji, do we agree? That's the main thing. If we're all happy, then you should be able to do the rest of these. Mr. Maraji agrees. Daishokusai agrees. Matt's kind of happy. So far so good. Jimmy's resident sleeper. Alright, Jimmy, give me the answers to the next three then, Mr. Resident Sleeper. And you can do the same thing here. What I'm going to do is on my calculator, instead of typing in the pi, I'm just going to do the 45 divided by 180. Because that's the only part I'm going to do, and leave pi in my answer of radians. So this is 0.25. Let's write it as a fraction. So this is going to be 1/4 pi, which we often write as pi by 4. Right? And if we backtrack a little bit and look at this diagram, so we just did 90 degrees as pi by 2. This makes heaps of sense, right? If this whole thing is pi degrees, or pi radians, sorry, this whole thing is pi radians, then what we know as 90 degrees is half of that, pi by 2. Yeah, yeah. Use the fraction key. I just convert it, but you're right. You should probably use a fraction. And same thing here with 45 degrees. I know 45 degrees is halfway between here and 90. So when we look at this is pi by 2, this must be pi by 4. Let's whiz through the last two and then let's get on with it. 130. I've just made these up. I'll do the fraction key so Mr. Maraji's happy. 130 fraction 180. Oh, there's my webcam gone now. It's been playing up, man. Let me fix it. 2 seconds. Is it back? What? I don't understand why it's doing this. Man, that's so annoying. It's back now, but I have to literally stand up, unplug, replug, and then deactivate, activate. So we've done this 13 by 18, so we can write 13, oopsies, 13 pi by 18. And the last one, 360 degrees. You can probably think about this. I'm just going to write the answer and let you think about that. Is 2 pi. Any questions on this? If you don't understand this, it's going to be hard for the rest of the lesson. This is the easiest part. Okay. If we're happy, we're going to move on. Spam chat if you're happy, or don't spam it. Rishi's happy. Right, we're ready to move on. Good. Now, I want to explain something to you guys, okay? I want you to really wrap your head around this. Have a think. This is a hard concept to understand. You need to focus while I explain this. Right? Let's have a look at something. Let's make a big set of axes like this. Let's bring back our trusty blue and red pen. Right. Let's say I plotted this on here. Hannah's here, yo. Right. Let's say I plotted this. Oh, let's go to this actually. This would be 4 and this would be 3. Okay. We're happy with this? Right. If we have this, then I could also say that the modulus of z would be the square root of 3 squared plus 4 squared, which we know would become 5. So I could quite comfortably put 5 on this diagram. And I'm going to use orange because that's what we were using yesterday. I could also, from yesterday, find this argument, right? Where the argument of z is going to be equal to tan inverse of the O 4 over 3. Which, do it on your calculator, double check. I've already done it. And I can say that the argument of z is 53.13 degrees, which is around about, let's just round it to 53 for now. Okay? Yeah, this is live, dude. This is live. Right. So I know that this is 53 degrees. Okay? Now, this is what we did yesterday, the argument, and this shouldn't be a problem. Now I want us to think about something. Let's pull out this triangle for a second. I want to make it nice. Oh. This is really important we focus here. Right. Imagine a scenario where all I've done is given you this information. Every day at 11 for the next 3 days or 2 days. Right. Imagine a scenario where I have this. I've got to focus on explaining this now. Right. Imagine a scenario where all I have is this, and I think, hey, I want to find this part and this part because I know that it'll form this, right? Where A is the real part and B is the imaginary part. But let's say all I have is the 53 degrees, the argument, and the modulus, 5. How could we go about getting back towards A plus BI? Let's just have a think, right? Because normal trigonometry rules apply. I'm going to give myself a little bit more room. See if I can move all this up here. Right. Let's have a look at A. Now soccer toes in the chat, right? So let's have a look. A is going to be the adjacent and the hypotenuse, so we're going to use ka. So for A, I'm going to use cos theta A over h, which means I can probably, I'll go very slow. Cos of 53 equals A, which in this case is our unknown, over h, which in this case is 5. Right? Let's rearrange it and say 5 cos 53 is A. I'm just going to leave it like that for a second. Right? 5 cos 53 is A. Let's look at B, please. Now B is going to be saw. And we're going to sine theta is O over h. Sine 53 is O, in this case is B. And h again is also 5. Which means 5 sine 53 is B. Are we happy with what I've done here? I just want to check in, make sure we're happy with Sokotoa. I've found that in this situation, with these numbers, I can find A by using cos and getting down to here, and I can find B by using sine and getting down to here. Please tell me if you're confused or if you understand. Matt's pretty happy, Hannah's happy, Rishi's ahead. We're good. Good. Maybe there's a slight delay between chat and me, so I see it now. Good. We're happy. Right. Now, we know that our complex number is in this form, A plus BI. So let's write A plus BI like this. But now I've got something for A and something for B. Let's have a look. I'm slowly running out of paper. Or not paper, but room on this thing. So A, we know, can be replaced with 5 cos 53. And we also know that B can be replaced with 5 sine 53. And we should put an I on there. Right? And there's a plus in between. I'll rearrange it in a second. Yeah, fair enough. Z equals A plus BI. And we've got this piece here. We happy so far? Let's work with this a little bit, right? 5 cos 53 plus, you happy if I just do this? Put this I in front. I know we don't often do it, but we're going to. Yeah, Miraji wants me to say Z equals in front of all of this, right? Now, I just want to work with these pieces just for a second, right? So, what's common between the two of these is a 5, right? You can see that there's a 5 common between these two. All of this is multiplied. All of this is multiplied, so we can pull out a 5 as a common factor. 5 times cos 53 plus I sine 53. We happy with that so far? This is year 13. Right. Now, what I want to do is have a look at this. This piece here, when we went back and had a look, this was the argument. Right? No, sorry, not the argument, the modulus. This was the modulus. Not argument, sorry, modulus. This was the modulus of Z. And how about this 53? Right? This came from the argument of Z. Both of these. You happy so far? So the modulus is the number at the front, and the argument is the numbers in between. That's the only thing that exists within what we've done so far. Now, mathematicians are lazy, and we don't want to have to write cos the angle plus I sine the angle every time we did this calculation. So we've come up with a way to make our life a little bit easier, right? Now, if I just generalize this for a second, bring this down, R times cos theta plus I sine theta. I'm going to change these thetas to orange. Okay, so this is what we call it generally. Now, R is just the same thing as the modulus. I think it stands for the radius, because if you imagine that this line was a radius and it spun around, but don't worry about that. Let's just call the modulus R for now. Okay, we've got this generally now, don't we? Because the argument is what goes in there, and the argument we call it theta, and the modulus is what goes in there, and we're going to call the modulus R. And Miraji wants a Z equals there as well. Okay. Now, like I was saying before, mathematicians are lazy, and we don't want to write out this cos theta plus I sine theta every time. So instead, we've come up with this. It's kind of weird, but it makes sense. R cis theta. Okay. Which cis stands for cos theta plus I sine theta. C-I-S, cis. Okay. So now we've transitioned. I know we've done a lot, but we've essentially transitioned from any complex number written in this form, a plus bi. We can get it all the way to this form, right? And now we have two different ways to write a complex number. This form we call polar form, and it's in the form of r cis theta. Jesus, exactly, right? Whereas rectangular form, oh yeah, Miraji spamming the z equals. You're right. And rectangular form is z equals a plus bi, or x plus yi, or x plus iy. And that's what we've got here in these more condensed notes. So any complex number, on the money, any complex number can be represented either or both and this way or this way. Where, let's have a quick think about this. I'll just scroll down like this. Where the rectangle, it's like we have two different bits of information. In rectangular form, we get given the coordinates of this point, and that's it. We can create this line. In polar form, we're not given any coordinates, but instead we're given a length and an angle, which creates that line. Right? We're creating the same line two different ways. That's why those two different ways mean the same thing. So in cis form, does I just disappear? No. I is here. Right? The I is in the cis. Right? It practically, I know what you're saying. Practically, you're kind of right, but technically, you're definitely not right. So you get what I mean? Because cis, by definitions, means I sine theta. Let's look at some examples to get our brains going. Okay? I'm going to erase all this. I don't really feel like it's needed. Okay? Right, let's look at a couple examples at this. Right, write these complex numbers in polar form. We're going to slowly work through these, because this is confusing, and you've got to grasp this. And you're going to hate me, because I'm going to give you lots of homework after this lesson. Let's look at this first example. Right? Z equals, or Z, you guys like Z, right? Plus I. Okay, let's draw the picture first, just to fully understand what's going on. And I recommend drawing the picture every time. So this root 3 on the real, is it on the right hand side, the left hand side? I have a think it's negative, so we're going to have, it's going to be over here somewhere, and it's positive I, so it's going to be something like this. Right? I might draw this a little bit bigger for you guys. Where this is root 3 and this is 1. Happy so far? Now remember from yesterday, this is the angle we can calculate, but this is the angle we want, because this is the argument. Right? So let's make a little triangle. I might even just go like this for a second. Maybe I'll do that in blue, because that's what we've been doing previously, right? Blue 2. There we go. So this is root 3, this is 1. Let's find this angle here. Yeah, we can just mute him, it's all good. Watch this. Timeout. Right. So we can do this maths here. The inverse tan of O over A, right? 1 over root 3. And we know that this is going to be the length of Z2. Theta equals tan inverse of 1 over root 3. Let's get out our calculator. With shift tan of 1 over square root, oh, it's really hard to see, square root of 3. Or am I in? I want to do it in degrees because I don't want you to get confused. There we go. 30 which means, I'm just going to move this up a little bit, which means that the angle we've calculated is 30, but the angle we want is 180 minus that, right? So let's go the argument of z. Oh, I haven't planned out this writing very well. 180 minus 30. Oh, there we go. Which is 150. Right, we've got the angle. What's the other piece we need for polar form? We need an angle and we need one other piece. I'll wait for you. I've kind of given you a hint there, but we need the angle and we need one other piece. Matt's there. The modulus of z, which I think is the easier one to calculate, right? It's the square root of these two squared, which in this case is going to be the square root of 3 plus 1, which is root 4, which is 2. So now, remember our cis form, or our polar form. We have r cis argument. R is 2, cis, the argument, is 150. And we've done the conversion, step by step. I should probably put this in brackets because that's how I've seen it in the past. We can even put a degrees there. Oh, sorry. It's gone past my face. How's that there? Not too bad. R by definition is the modulus. It comes from the radius, because if you created a circle out of that, that would be the radius. Because you're like the polar form is all about a circle, right? It's around a pole. So if you imagine, I create a radius and an angle that I twist through, you can get anywhere, any complex number. Most people are happy. Kate's happy, Isaiah's happy, Matt's happy, Hannah's on board. Cool. Can you start the next two? I'll fill up my drink, and then I'll come back and do the next two. Right? You want time to do it? Z equals. I'm gonna forget that this whole lesson. I can just see it. I can just see it coming. Trigger's kind of ugly. Trigger's more ugly if you don't draw a diagram. Right? If you draw the diagram, your life is so much easier. I promise you. So for the next two, start the diagram, draw it. I'll get a drink. I'll be back in 1 second. Right? Right. Someone better have an answer for me. Too quick. You're joking. Come on, man. Let's look at this next one. S equals minus 12i. Let's draw the diagram and go piece by piece. Minus 12i is just going to be down here, isn't it? I keep drawing small. Let me draw bigger. Minus 12i is just going to be here. So if I created a complex number like this, I can already think about the angle straight away. The angle I turn through is going to be minus 90 degrees. Kate, not achieved. Minus 90. Okay, it's got to be minus 90. Okay. And in radians, please give me the radians. And then I'll calculate the modulus while you guys give me the radians of minus 90. Oh, we're not doing Z, we're doing S. Got ugly, but it's okay. 12 squared. You see the importance of the diagram? Exactly. Exactly. Right, we got minus pi by 2 in the chat. Good, I agree. Minus pi by 2. So this we could write as r. We've also got theta is minus 90, or theta can be minus pi by 2. So therefore, here you go, sir. S equals 12 cis. I'm going to do it in radians just to annoy you guys. Minus pi by 2. So far so good. Right? One more and then we're going to do the reverse process, which I think is a little bit harder. Mr. Maraji, do you think it's harder to go back from polar form to rectangular form? Let's do this process very quickly. I already know that my angle is 0 in this case. Oh, it needs to be W, doesn't it? Mr. Murray doesn't think it's harder to go the other way. I thought it's harder, but maybe I'm just not as wise. Did you guys get 6 cis 0? Webcam. The webcam's fine. I was just standing still. We're happy. Now, Miss Maraji, please tell me if there's a different way I should write this. If I should write cis 0 as a different thing. Because cos of 0 is 1, sine of 0. Yeah, so you could just write it as 6, I'm sure. But, oh, I was blocking it. Sorry. I've scrolled up now. Yeah, Maraji, let us know if that is written, if you're happy with how to write that while I start the next example. I want you guys to give this a go a little bit. Let's look at example 2 and we're going to work backwards. So Z equals 2 cis 120. Right, focus on this please. This is important. Right. Because we are smart, and you've heard it me say it 1,000 times, we're going to draw the diagram first. 2. Okay, so 2 is the length. 2 is the modulus. So whatever complex number I have, it's always going to have a length of 2. Okay? Right. Now, 120 degrees is the angle I've turned through from this axis. Right? From this axis, we have turned 120 degrees. If I turned this far, I would have 90. And so if I turned all the way to here, I'd have 180. So it's going to end up in this quadrant. and we're going to have some complex number that has turned 120 degrees. Its length is 2, but the angle we're going to use in our maths is going to be what, please? This angle here is going to be 60. Good. Okay? Because we turned through 120, but when we create our triangle to help us with the calculation, you can see we always need the inside angle, right? So you can see that this angle is going to be 60. And we also have this length of 2. Happy? Now remember, A plus BI, right? A is always going to be this bottom side, and B is always going to be the opposite side. And you could even scroll all the way back up to your definitions of A and B over here, where we found that A was r cos theta and B was r sin theta. But let's do it manually first before we take any shortcuts. Okay? So if we have a look at this, let's do B first. We've got O and we've got H, so we're going to use SO. Sine theta is O over H. I know I'm taking lots of steps in this one. Okay, I'm going to speed it up in the next one. 2 sine 60. 2 sine 60. On your calculator, 2 sine 60. Fax is right. Okay, fax is right. Oh yeah, 1.73 is the same thing as root 3, because I just know that because I'm smart. Okay, what is 1.73, which I know is root 3. And I can also look at A is going to be cos theta is A over H. Cos of 60 is A over 2 cos 60. 2 cos 60 is 1. So our A plus B sine is going to be 1 plus root 3i. Tell me what I've done wrong. Yeah, Mr. Murray, you're right. I'm going to get to that in 1 second. I just want to do this and see what I've done wrong. Tell me what I've done wrong. Using 60 in this case is fine. Z equals, you're right, but that's not actually what I'm looking for. Yeah, Matt's talking about some negatives, right? Okay. We look back at this. We can look back at our diagram and use some logic and think about this, right? We've ended up here into this negative zone, which means that our real number must be a negative number, which means that our actual answer for Z is minus 1 plus root 3i. Okay, but now we're going to go into what Mr. Maraji was saying, which is significantly easier, but I want us to understand what's going on here. Right? 2 cos 60 is that. You might not be in degrees. Yeah. Go shift, set up, go to degrees. And you'll get it. Let's do the same question, but in a much easier way. Okay? So the same question, let's have a look. We've got 2, we've got z equals 2 cis 120. Right? Now, let's back up. We know that this actually means 2 times cos 120 plus I sine 120. You with me? Where this chunk is A, or I might just go, this chunk multiplied by 2 is A, this chunk multiplied by 2 is B, so we can do 2 cos 120 plus I times 2 sine 120. Right? Which is so much quicker. But I want us to understand the context of what's going on. Right? And this will produce the correct negative values because of how cos and sine work. Right? Now her calculator was in radians, that was the only problem. Go shift menu. So if you type this in, let's type this in exactly as I see it. 2 times cos 120 minus 1 plus 2 times sine 120 1.73 and there you go. Which we're basically using the definition of cis to produce this. The definition of cis. Any questions? I'll wait. Ah, I knew. I told you. I'm going to forget this the whole time, sir. I told you. We're good. Right. Okay. In this example, we use 60 because we used the diagram and the definition of a triangle. Right? But in this one, we're using the definition of what cis is. And cis uses the argument. Right? So cis is cos of the argument plus I sine of the argument. So therefore we can always use the argument. I recommend always doing it this way that you see here. So let's use this way to produce B. Or to work out B, please. Yeah, we should make Z equals as an emote. You're right. Right, Q equals this question. The argument calculation is much easier. You're right. So I've shown you the hard way so that you're grateful for the easy way. Okay. Right, let's do this. So by definition, this means root 3 times cos of minus 3 pi by 4 plus I times root 3 sine minus 3 pi by 4. Okay. Good. Daishokusai. You've got to change the radians to degrees. Either in your calculator you can do it, or you can do it before you do it. Before you type it in. So to do this, I'm going to pull it out over here and do it. Minus 3 pi by 4. We want to convert this to degrees. To do so, what did we say? What is pi in terms of radians? Pi by definition is 180. Right? So to convert it to degrees, we can just say minus 3 like this. Because pi by definition in degrees is 180 degrees. So we can replace pi with 180. Let's calculate this. Oh, I should do it on screen. Minus 3 times 180 over 4 is minus 135. So now let's make this question even easier. I'll just move this across. Move this across. Let's say Q equals. Therefore Q equals root 3 cos of minus 135 plus I times root 3 sine minus 135. Type it in, let's see what happens. I'm expecting some chat spam in a second to tell me what the answer is. Root 3 cos minus 135. Is this here? Minus 1.22 plus I times, or let's put the I at the end, root 3 sine minus 135. Same answer. No, it's a good question, Isaiah. It's a good question. The reason why you can is we've now learned what a negative angle means, right? In real life, you obviously can't ever measure a negative angle. But if you think about what a negative angle means, it's implying the direction that you're turning through, right? So it means that the negative angle, we measure it from that axis and we're rotating clockwise underneath. We're going negative. And that's why you can have the sign of a negative angle. But it's a good question. It's a fair question. Last one, and then we're done. I'm super hungry, so let's get this done quickly. Oh, yeah, I had U equals. I was about to say, oh, I missed it, but I had it. U equals. I had Q equals correctly. Cis of 0. Okay. Now, again, you could think about this. You could draw a picture. We could do it by definition. For ones like this, I want to just think about it like this for a second. We've got a length, and we've turned through nothing. So this is very easy to do a plus bi, isn't it? Right? My real component is root 5, and my imaginary component doesn't exist. We're done. Now, I reckon that this is slightly harder than yesterday, because it incorporates everything we did yesterday with added pieces. But if we understand the argument and what it is, and we understand, the key part is to understand this definition, right? That cis is, you see here, cis is cos theta plus I sine theta, where theta is the argument and r is the modulus. Theta is the argument and r is the modulus. So it's mod cis arg. Mod cis arg. Excellent lesson, sir. Thank you. Right. Just leave it as root 5, man. We don't need to do anything more with it. Root 5 is fine. Do you save these videos? These videos get uploaded automatically on here. So you can go twitch.tv/nutshellmaths/videos and it'll show you all the previous broadcasts. So you can see yesterday's video on there. Hannah, thank you for the follow. Right, here's your guys' homework. Now, I'm telling you this right now. I'm going to be super honest. When I took calculus at high school, I didn't do homework. I was lazy as hell. Right? I didn't do well. I passed a couple standards, but I struggled to understand this conversion because I didn't do it 15, 20, 30, 50 times. I did it like 3 times and I was like, oh yeah, I think I get it. And then 2 weeks later, I lost it. This needs to be a process that you can just do. So, in order to be successful, you're in isolation, you've got nothing else to do, please complete all these questions here. It is on our Google Classroom. It's all there. Can you please make sure you do this? I'm obviously not going to check it, but if you want to be successful, there you go. You have more than one subject, you know. I do know, but you also have an infinite amount of time. Yeah, Jimmy's right. Jimmy's tip is good. It is on Google Classroom, right? Let me show you. Look at this, Google Classroom. Complex numbers in polar form. You click here, scroll to the bottom, boom, it's all there. Also, yesterday, argument of a complex number. The notes are there. And the worked answers from yesterday too. Basically everything we did on stream. It's all there. You have no excuses to be successful. Remember, I've put in heaps of effort. I put in, for every hour I do, I'm putting in another hour behind the scenes. Right? Easily another hour. So I've spent easily 1 hour preparing this lesson, which means you can spend easily 1 hour following up on this lesson. Okay? Can I do example 4 from yesterday? No, I can't be bothered. I'm too hungry. It's been 53 minutes. Right? I told you the answers. It's a show me. It's a prove question. Jimmy's given you a tip. He said, for example 4, what was his tip? The real equals the imaginary. Right? It's all on Google Classroom too. Right, is there any questions, anything like that? Kate's got the answer too, so you can message her, find out. Are we happy? We're feeling successful? Feeling like we can go away, do these problems? Gonna eat some leftovers, is that? Leftover stir fries. Tina's spoken up, she's happy. Hannah's happy. Felix is going for it. Thank you, not thank you. It's in my personal Google Classroom, but it's also probably on Mr. These questions are just out of the Delta textbook, which you can find on the maths website as well. So 32.1. Cool, thank you guys so much for tuning in. I really appreciate everyone coming. It makes it genuinely worth it for me. Right, HSL signups, we'll talk about it another time. Same with the RM20. Good stream, thank you, Pearman. Thoroughly helpful. Good to hear. Right, I'm going to head off. I'm going to eat some food before the year 11 stream. You guys work hard. We've got one more important thing tomorrow. Basically, tomorrow we're going to cover why... Hey, Rebecca's here. Basically, tomorrow we're going to cover why this is important. Okay? Why this thing that we've just learned is important. Or what use it's for. Right? Thanks, Matt. Have a good one too, dude. Alright. See you guys tomorrow. Thank you so much. See you later. Oh, wrong one. That one.